Hi everyone. So today we will be talking about what a random forest is and how does a random forest classifier actually work. So in essence, random forest is basically it's a team of decision trees which are working together to make better predictions. It belongs to the family of what we call as ensemble learning algorithms, which means it combines multiple models to produce a strong or a stronger overall model. And let's try to understand the core concept with an analogy. Like say imagine you're trying to decide which movie to watch. And instead of asking just one friend, you ask 10 friends because one friend might give a biased opinion. So you go with the movie that the most friends have recommended. So in this case, each friend becomes a decision tree. Each recommendation is a prediction or a class. Final output of the prediction is the majority vote. Now, the step by step of how a random forest classifier classifies is basically done in three different steps. First, you build many decision trees. A random forest builds multiple decision trees, each trained on a slightly different subset of the data, and these subsets are created using random sampling. And this random sampling technique is what we call as bagging. This is a bagging algorithm. At each split in that tree also chooses a random subset of the features to consider. So this helps to bring in the diversity that is required, which is absent in general decision trees. Now, when a new data point is given, like say some information about the length of the tail, the length of the nose, or length of the ear, whatever data is being trained on, whatever data the model is being trained on, each tree makes its own prediction about which class it belongs to. Example, whether it belongs to a cat or a dog or a rabbit class. And then the predictions from all of these trees are counted, and the class with the most votes, it becomes a final prediction. So that is the basic step-by-step understanding of how a random forest is going to classify. Now, let's say we have a random forest with 5 trees and we give it some information of an animal to classify. That information could contain the length of the tail, the nose length, the type of fur it has. So we will see that there are these 5 different trees will give some sort of prediction. Each tree will give like, since the first tree will give a dog, second tree cat, third would also give a dog, fourth will be also a dog, and three number 5 will also give, say, a rabbit. Now here dog got 3 votes, so which is more than any other class. So that's the final classification. That is, this particular data is being classified as a dog. Now, the number of trees, the number of random forest with 5 trees, the number of 5 trees that we have here is basically given by a hyperparameter called n underscore estimators. This is what determines the number of trees that will be acting to predict classification result. So that's what the random forest is all about. It's basically like a democracy of decision trees. Each tree has its own say, and the class with the most votes will win. So that's how random forest will work. Now, node splitting is the underlying principle of how a random forest is working in the backend. So in a decision tree, data is split at each node, based on the feature that best separates the data into distinct classes. And in random forest, each tree splits the nodes, but with an added twist to make each tree different. And that added twist is technically the random feature selection. So instead of looking at all features to decide the best split, random forest will choose a random subset of features at each node, because this is going to add variety between all the trees. Every tree will be different. That helps to reduce overfitting and basically increases the accuracy of output of the model. And among these randomly selected features, the algorithm calculates the best split using a certain criterion. Those criterions are like Gini impurity or entropy or information gain. Now, Gini impurity is something which is used, most commonly used in classification problems. And, some of the trees would, and entropy and information gain is used in some trees. So now, for example, let's say you're building a tree to classify animals, like you say cat, dog, rabbit, and you have some features like, you have the size, you have the ear shape, fur length, tail length, and, at any given decision node, random forest is going to pick up some features, say ear shape and fur length. Maybe it'll pick 2 out of the 4 features, or it depends. Randomly it'll pick out those features, and it checks different ways to split that data based on those 2 features. Now, in the backend, for each possible split, it will calculate the Gini impurity. And for that, we have this formula here. It's Gini is equal to 1 minus the summation of the proportion of the class in that split whole squared. So this is what is basically happening in the backend. Now, you see the root node. Every root node can be split into a decision node, and every decision node can be further split into another decision node or a leaf node. A leaf node is that node where no more splits are possible. But if there's a decision node, it can be further split. And this splitting will happen all the way until all the last nodes are leaf nodes. And if all the leaf nodes are of the same class, then we can call it as a pure class. So That's how it runs in the backend, and this will continue to happen. This will happen again and again until the tree stops to grow because a stopping condition has been reached, and that stopping condition is technically you have reached the max depth, which is set by a hyperparameter in your Python code, or it has reached the minimum number of samples in a node, or the node becomes pure, like all data points belong to one class or to the same class. Now each node will continue to split, and it will repeat until the random forest is going to randomly choose those features. It will find the best split, it will divide the data, and then reach a stopping condition, and until it has found its pure class, or it has found the correct classification node. Now why does random split help? Why do we need the random sampling in a random forest? It's because by forcing each tree to pick random features from your data set, the tree learns different patterns, which makes the forest diverse, and it basically helps the ensemble to perform better than any single tree. So you will have diversity, so you're able to learn more patterns from the data set, and then you'll be able to come to a better classification. So let's recap. At the first step, the random subset of features is picked at each node, and then the best feature and threshold is given using Gini or entropy calculation that we studied in the previous slide. And then that data is split into different child nodes, and if that child nodes can be further split, it will be split, or it will turn into a leaf node, which is basically containing the classification data of whether it's a cat, whether it's a dog, or whether it's a rabbit. And this will continue repeatedly until the tree grows, until a stopping condition is met. So with this, we can move on to quick Python example of how to implement a random forest, and we can use it on a similar data set. So let's move on to our collaboratory. So let's move on to our Python and Jupyter notebook, and we will be using Google Colab for this. Okay, so we're here. I've already done my imports. I'm importing pandas, and I'm importing from the sklearn scikit-learn library. I'm importing Random Forest Classifier, which is going to be a main algorithm that we'll be running. And then I've got some train test split methods from model selection, and I'm going to use label encoder to label encode my target variable. And then we've got classification report and accuracy scores for checking how well our model is doing. And we've got Seaborn and Matplotlib for some of our visualizations that we'll be doing. Let's go ahead and run this. And then I've got this data set called animal classification.csv. So let's start with bringing it in. I'm going to read the CSV and say animal underscore classification.csv. And let's see the head of the data set. So you can see there are 6 columns, unnamed 0, ear length, nose length, fur length, tail length, and you've got the target variable called animal. You can see most of them, all of them rather, other than the target variable, are numeric features, and maybe these describe the length in centimeters or maybe feet or whatever the unit could be. And the animal is a categorical variable, cat, rabbit, dog. So let's look at the size of a data set that we have. This is 10,000 rows approximately, including the zeros of 10,000 rows with 6 features. Now that 6 feature is an unimportant feature. It's not really required, so we will be dropping that. So we can start with simply visualizing the data set. We can use some sort of a pair plot to see, but before that we can set the Seaborn style. So we can say set style, and let's say white red, and then we can do a pair plot, sls dot pair plot, and so you can see here that the data could be any. In this case, we are doing a data frame. So we said data is going to df, and the hue is going to be the class type. So the class type in our case is animal, and we'll set the height of that figure to say 2.5, and let's give it a color theme, which I will say set 2 because it's sort of subtle and nice. And then we can give it a quick title and say feature distribution by animal type. So that would be my title. And then let's go ahead and see what that is. This will take a little while because we have a large data set, about 10,000 rows, but I can fast forward it. There you see. So we've got a pair plot coming in, which is basically talking about the basic density of each of these things. Now this unnamed is something gibberish. We don't have to worry about it, but let's look at the other things. Ear length, nose length, fur length, and the tail length. Now with unnamed 0, it's okay. We can skip that part. We can actually even drop that feature first and then create this plot, but let's concentrate on the main part. So you can see here that the ear lengths are they're pretty homogeneous clusters, and they have a fine definition, and most of the data points are pretty well clustered. So you can see that the ear length, we can expect rabbits ear lengths to be slightly longer than cats and dogs, with the cat having the smallest of them. And you can also see the same thing in this histogram sort of a ADE plot, where you can see that the distribution for a rabbit is on the left side, and it has a higher amplitude, suggesting a larger variance in the data as compared to the cat and dog. And similarly, if you look at the tail length, we can expect perhaps, according to this data set, that the variance is high, but the overall length can be shorter. The width of the amplitude is high, but the width of this curve is short of a rabbit as compared to a cat and a dog. So these are the kind of features and their variances that we can observe in this chart. But you can clearly see that a rabbit has a very defined set in the tail length. This is pretty different from the cat and dogs. While the cats and dogs generally are showing similar sort of features, similar sort of range, but still a homogeneous cluster can be discerned here. Now let's go back down and see how we can create the target features and encode the target variable. So let's start with encoding. So we encoding the target feature. So we've got, let's set up LE equals label encoder. I'm going to set up a class, an instance of the label encoder thus, and I'll say df of target. I want to encode the target variable as df of target, and we set that to array.fit underscore transfer. You can see it's already given us the whole thing. So yeah, let's do this. DF animal, and then you can drop off the animal because you don't. So this is basically code completion here. So we are going to df to drop the animal because we've already converted into the target variable, and we will now run this with in place is equal to true so that it works on inline. If you don't want in place is equal to true, we can remove that and set df equals this. It's going to be the same thing. And now let's take a look at what we see. So it's encoding all of those 10,000 rows. So this might take a little while. And now to see, you can see now all of the variables have, they've converted back. Now at the same time, let's just remove this as well. So let's say df equals df.drop, and we want to remove this feature, which is absolutely not required. So let's remove it right now and place it over here and then say axis equals 1. And then let's look at that thing again. So you can see that unnamed 0 is gone, and we've got target set to 0 to 1. Now we don't know which one is, how do we know which label has been assigned to which class? So to figure that out, we can simply write a small for loop that will iterate through our data set. So for I, comma label in enumerate, let's say, what are we enumerating? We're going to enumerate the LE classes. So LE dot classes underscore. This is the class which contains the encoded features. And we can say print just for us to know which part is what. I'm going to say print the label the label is equal to the value I, and let's print that. So now we can see that cat is 0, dog has been assigned 1, rabbit has been assigned 2. Now the next thing is going to be feature and target selection. So let's do the feature and target creation, and I'm going to call it x equals. Now I want to create so this is the best way. Now I'm already getting it. df.drop target axis equal to 1. This is the best thing to do. We already have. So I'm going to drop everything in the x. I'm going to drop all of these. Sorry, I'm going to retain all of these and keep just the target in my y. And I'm going to drop the target and just keep all of these in my x. So these are my features, and that's how I'm setting up the target. So once that is done, let's go down and split it into train test. So again, you can see code generation is already giving us, it's already able to understand. You can simply press a tab here and it's splitting it into an 80-20 ratio, 0.2. So test size will be 20% and the train size will be 80%. So let's go ahead and run this. So now that split has happened. Now if you actually see x underscore train dot shape, you'll see that it has been split into, say, this is sort of 8,000. And if you look at the x underscore test dot shape, that should give us something like 1999. Oh, 2000. Yeah, of course, this is not started from 0. So you can see now that's a perfect 80-20 split of 10,000 rows. So moving forward, let's create the instance for the random forest classifier. And we are now going to set the n estimators equals 100 and random state to 42. Now the n underscore estimators is basically nothing but the number of trees, as we have already established when we were going through the theory part. This is the number of trees that we're going to decide. So I'm going to keep that to 10 for now. And just we give it a random state, say 22. That's my birthday. So let's keep random state as 22. And then we will fit this model, our dot fit, and we'll fit this on our x train and our y train. Okay. So this fitting is done. And now we are going to run a prediction by saying y thread equals rf dot predict. And we're going to predict it on the x test data. So that's the prediction there. And then now the prediction is done. So if you actually see what bypred is going to give you some sort of an array of what it has predicted in the x test set. But right now it won't make a lot of sense. But let's go ahead and test this. Well, how well it has done on, how the model has been doing. For that, we'll have to do something called as an inverse transformation. We need to see what those labels are in these, in this arrow. So let's say, for example, I'm going to say y thread when the labels will be given by le dot inverse underscore transform, and I'm going to transform that all by thread, and I'm going to copy the same thing again and set it to say y test labels now. Y test underscore label, I'm going to put that on test. So we've got two new variables which will contain this. Now let's try to figure out and evaluate our model. So we're going to evaluate model metrics, evaluate the model. So let's see what the accuracy score is. Let's print the accuracy score. Accuracy is, let's say accuracy. Okay, this is going to be a f-string literal. Accuracy underscore score in brackets. Now I'm going to compare the information I got in the y test with the ones that I actually predicted by print, and then I will print it. So I can see here that the accuracy is 0.919. That's almost 91% accuracy on the test data set. Now let's create similarly we can create a classification report, and for that we can just simply say print the classification report on the same y test and y predicted. So you can see here that we have a table which tells us the precision for each label. You see the rabbit has been almost perfectly and correctly determined. It has a 100% precision score, a 100% recall score, and a 100% F1 score. But it might not have been very accurate with dog and cat, because if you remember going up and seeing this, the homogeneity and there are a lot of overlaps between the cyan and the blue dot. Yeah. So there has been some sort of a slightly lower precision and recall for these two classes. Now let's see how well this has compared. What is the fit of a model? We need to know how well that has done. So let's see. By train thread equals rf dot predict on extreme. I'm going to predict this thing on the extreme data, and then I'm going to check the training accuracy. So let's say training accuracy equals, I'm going to set up the accuracy score again, and this time we will match the y train and the y train thread score. Okay, and same thing we're going to do for test. So the same, it will be test accuracy equals accuracy score between y test and y thread. Okay, and let's create a quick visualization of what we're going to see. So let's create a figure, and we give it a fixed size. We add the values in a tuple, say 10,6, and then we say SNS dot power plot, and we want to give the x values in a list, and those will be that of the train accuracy, the test accuracy, and then we will give it the labels. So let's say y equals, I'm going to give the labels of training accuracy and testing accuracy. So you can see it has actually auto-populated the entire thing all by itself. But let's say we don't need this part, and let's run this. So you can see here it's very clear that the training accuracy is slightly shy of 100%, probably 0.99, and the training accuracy, as we can see here, is 91%. So that's what we are seeing over here. So I can probably say that this is a slightly overfitting model, not the best, but yeah, I mean 99% as compared to the 91 on test. So we can actually see how each performed by simply printing off these scores here. You can see I'm going to say print training accuracy is trainac, and the testing accuracy is, say this is testac. Let's run that thing again. Now we'll be able to actually see it in numbers. So yeah, there you go. To 99% for the training, and testing is 91%. So there's a decent gap. So there's about 9% gap, which tells us that this is a slightly overfitting model. Now let's try to figure out how this data works on, or this model works on some unseen data. So what I'm going to do is, let's say we have a new data, and I'm going to say, but before that, let's add this. Let's quickly look at the columns again. So I'm going to see the head of our data set, and yeah, let's go for the new unseen data. Is say ear length is I'll say 11.5, and the nose length, let's go for 9.5 centimeters, and the fur length can be 2.7, and let's go for a long tail, say 5.23. So at this point I should be expecting maybe the classification to be that of a dog because of the longer tail length. So now how do we use the model on this data? What I can do is convert this data into a data frame first. So let's say td dot data frame, and I'm going to pass in since I'm passing a list, it's a scalar quantity, so I'm just going to set in data out here. So if I just see the TDF right now, this is what I'm going to get. So we don't know what is what. So I want to rename these columns here. I'm going to say TDF dot columns is equal to, and then I'll give it ear length comma, nose length. We have to ensure that this is in the right serial order, just like we have in our data set above. And then finally, we've got the tail length. Okay, and that's a TDF column. And now on this data set, we are going to predict answer. So let's say what this gives us now is a proper data set which has the right features labeled proper. So ear length, nose length, fur length, tail length, and we've got the values that we've just entered, some unseen value which the model has never seen before. Now let's go for prediction. So let's say prediction equals, and we're going to use our model RF, and then we say predict on this TDF, this data frame that we've just created above here. And before, so right now it will say prediction. Let's see what it says. Prediction is that of array 1. So 1, if you remember, was when we label encoded it, if you can recall, 1 was a dog. So we were expecting a dog and we got a dog. Now, how do we can further refine this? Like we can just write an if loop, like if prediction, if the prediction value equals 0, then just print it is a cat. And then you can simply copy this entire thing, Control C, Control V, and say if prediction is 0 and if the prediction is 1, call it a dog. And if the prediction is say 2, then call it a rabbit. Now, why 0, 1, 2? Because again, let's go back to the training, the label encoding, and you see cat was 0, dog is 1, rabbit is 2. I hope we've done the right. Cat was 0, dog is 1. So cat is 0, dog is 1, rabbit is 2. That's correct. Now let's just run this and you can see that's the final outcome. So if I simply run this again, let's just put it over here. I'm going to remove this and I'm going to cut this back into place over here, and I'm going to remove this as well and put it over here. Okay. Now let's predict this on our new data. So I'm going to change the data now. I'm going to shorten the tail length. Let's use something like maybe a small furry tail, say 2.24. Now we should technically get a rabbit out of this. Let's see what we get. So the moment I zoom, there you are. We have rabbit as a prediction, which basically means that the prediction value must be array 2. So now we know that the model is predicting with this information of ear length, nose length, fur length, and tail length. Our model is predicting with 91% accuracy that this is a rabbit. So that's all for this session. This is how a random forest works. It's a proper working code that demonstrates how random forest classifier works.